Welcome back to the Deep Dive, where we take complex research, dense engineering data, and structural mysteries and just distill it all down for you.
And our mission today is foundational. I mean, that literally, we are getting into concrete.
We are, specifically a piece of research from Peruvian Union University by Max Ramos and Edwin Perillo. Their goal was to figure out how to reduce cracks in concrete slabs by adding polypropylene synthetic fiber.
And, concrete cracking, it sounds so mundane.
Right.
But it's a colossal problem with a huge global price tag.
Mm-hmm.
The sources we looked at point to places like Colombia, where standard concrete can be so weak that something like 90% of slabs need expensive sealing just to hold up.
90%, that's almost a guaranteed failure rate.
It's massive. And the researchers noted that locally, in Peru, it's often an ignored problem. It's seen as a long-term issue, something for later.
Kick the can down the road.
Exactly.
Right.
But that just guarantees serious structural decay over time.
So the hunt is on for a fix, something accessible, sustainable, and that doesn't break the bank. And the idea here isn't to reinvent concrete, but to improve its internal cohesion, especially while it's setting.
And that's where the polypropylene fiber comes in. But before we get to their results, we have to talk about the existing landscape of fiber reinforcement.
Yeah.
Because it has this history of both amazing promise and, peril.
Okay, so let's start with the promise. What kind of numbers are we talking about?
Well, prior studies have shown some really phenomenal improvements. You get confirmed benefits to tensile strength. That's the ability to resist being pulled apart.
Right.
That can increase by up to 24% with just 0.5% of fiber. Other research saw compressive strength, how much weight it can bear, jump by an incredible 46%.
46%, that's huge. So the fibers are acting like microscopic bridges.
That's a perfect way to put it. They improve ductility, and they stop tiny microcracks from linking up and becoming big problems.
Okay, that sounds like a miracle additive. So what's the catch? This must be where the peril comes in.
It is. This is the core conflict of the research, what they call the dosage dilemma.
The dosage dilemma.
Exactly. You'd think if a little fiber is good, a lot must be fantastic, right?
Seems logical.
But the research shows the opposite. The optimal amount is absolutely critical. Once you go over a certain limit, maybe around 1.5 kilograms per cubic meter,
okay,
the fiber stops helping. It actually starts to interfere with the mix. You get more porosity, not more cohesion. You're basically introducing millions of little things that get in the way of the cement paste bonding.
So you can actually cause cracks with the very thing you're using to prevent them.
You can. It's a very fine line. We saw other studies where too much fiber cut compressive strength by almost 16%. So the researchers here, they weren't just asking if fiber works. They were trying to find the one perfect dose that helps across 3 key metrics.
And those were?
The total number of cracks, their width, and their length.
Got it. And they used a pretty standard concrete strength, 21 FSC, and tested 4 different mixes.
Right. You had the control, MP, with 0 fiber. Then DM01 with 500 grams per cubic meter, DM02 with 1,000 grams, and then the high dose, DM03 with 2,000 grams.
So let's get into how they actually tested this, because the methodology here is pretty clever.
It really is. They ran into a roadblock right away. In Peru, there just wasn't a standardized test for this kind of long-term drying shrinkage.
So no local yardstick to measure against. What did they do?
They adapted an American standard, ASTM C1579. But, and this is the key, they used it in a totally different way. That test is normally for plastic shrinkage.
That's the cracking that happens in the first few hours, right? When it's still wet.
Exactly. It's a short-term test.
No.
But they stretched it. They extended the evaluation period out to a full 35 days.
That's fascinating. So they took a test for immediate survival and turned it into a test for long-term durability.
Precisely. And the physical models they built were just as smart. They cast 20 specimens, 5 for each mix. And they were very particular about the formwork. They used phenolic wood boards.
Hang on. Why does the type of wood matter?
Great question. Regular wood soaks up water. It would have pulled moisture from the concrete and completely skewed the results.
So it wouldn't be a fair test?
Not at all.
Yeah.
Phenolic wood is non-absorbent. This meant the only water loss was from evaporation into the air, which is exactly what they wanted to measure.
They were isolating the variable, and I also saw they built in weak spots on purpose.
They did. The formwork had these raised sections, which made the slab thinner in certain areas. They were concentrating the stress, basically daring the concrete to crack in those spots.
So they could measure exactly how well the fiber fought back.
Yes, and the curing process wasn't in some perfect lab tank either. It simulated a real construction site in Juliaca, Peru. daily watering, a moisture cover, average temps around 11.5 degrees Celsius. Then they measured everything by hand.
And what did that long-term observation tell them?
Something crucial. That a lot of the big final cracks didn't just appear. They formed from smaller, linear cracks, merging over time as the slab kept shrinking.
Okay, so let's focus on that immediate impact. The first 4 hours, when the concrete is most vulnerable, this is the plastic state.
Right. Here they used the C1579 test, as intended, comparing the control mix against their most promising dose, the DM02 at 1,000 grams.
And they were measuring water evaporation. What did they find?
The results were pretty striking. The control mix, the one with no fiber, it lost water at an alarming rate. We're talking 6.32 kilograms per square meter per hour over 4 hours.
6.32? Is that a lot? Put that in context for us.
It's an extreme amount of water loss. It's like leaving the slab to cure in high winds or under a heat lamp, conditions that almost guarantee cracking.
A worst-case scenario.
A very worst-case scenario. But here's the kicker. The fiber mix, DM02, it reduced that water loss by over 20%. It was only losing water at a rate of 5.05.
20% is a huge difference in those first few hours. So the fiber is what? Holding the water in?
Essentially, yes. It's slowing down the drying process. And that had a direct effect on the cracks. At just 2.5 hours, they saw a 71% reduction in crack length.
71%.
And a 50% reduction in the number of cracks. Even the crack width was down by almost 13%.
So the mechanism here is that the fibers are physically blocking the water's escape routes.
Exactly. They interrupt these tiny capillary channels. They're like millions of tiny dams, holding moisture in so the cement can hydrate properly. It's a powerful first line of defense.
That confirms the immediate benefit, but the real question is about long-term durability, right? What happens at 28 days when the concrete is supposed to be at full strength?
Right. This is the true test. Does the early advantage hold up? This is where they applied their crack reduction ratio formula to find the absolute optimal dose.
Okay, let's break down that 28-day data, starting with crack width. You could argue that's the most important metric for a building's lifespan.
I would agree. And here, the DM02 mix, the 1,000-gram dose, was the clear winner. It achieved an 18.41% reduction in crack width.
And the lighter dose?
The lighter dose, DM01, was okay, but an 11% reduction. Good, but not the best.
Now, what about the high dose, DM03? Common sense might suggest more fiber means tighter cracks.
And common sense would be spectacularly wrong here. DM03 was a catastrophic failure on this metric. It didn't reduce the width. It resulted in a 28.75% increase in crack width.
An increase? It actually made the cracks wider. Why?
It all goes back to that dosage dilemma. A high concentration of fiber it got in the way. It ruined the concrete's workability. It created voids. And when the slab shrank, those defects opened up into much wider, more dangerous cracks.
The concrete basically rejected the reinforcement.
It did. It makes that middle dose, the 1,000 grams, look like a really delicate sweet spot.
Okay, so what about crack length? Stopping a crack from spreading across the slab.
This is where it gets even more interesting. Again, DM02 was the star. In fact, it was the only mix that reduced the crack length at all.
The only one?
The only one. It achieved an 11.46% reduction. Both the light dose and the heavy dose actually made the cracks longer than the control.
So the other mixes were failing on two key metrics. What about the final one, just the raw number of cracks?
Here, finally, the high dose, DM03, delivered. It had the biggest reduction in the number of cracks, over 43%. DM01 and DM02 were also good, with reductions in the 30s.
Okay, so there's a clear trade-off. The high dose gives you fewer cracks, but the ones you get are much wider and a bit longer. Why is that a bad trade? From an engineering perspective, isn't fewer cracks better?
No, because width is the real killer. Width is what dictates how fast water and chlorides get into the concrete and start corroding the steel rebar inside. A few very wide cracks are like open highways for corrosion. Many tiny, tight cracks are much less of a long-term threat.
So a wide crack is a direct path to structural failure.
A much faster path, yes. So while fewer cracks sounds good on paper, if they're 30% wider, you've actually just designed a structure with a shorter lifespan.
Which means the researchers landed on DM02, the 1,000-gram dose, as the clear winner. It's the best all-around performer.
Without a doubt. It provides the optimal balance. A solid reduction in width, in length, and in number. It's the best overall integrity profile.
All right, let's bring this out of the lab. What does this mean for a contractor on a job site? Is this solution just too expensive to be practical?
Well, cost is always the big question. The researchers did the math for their local market in Peru. Adding the optimal DMO2 dose cost about 40 sols per cubic meter.
And 40 sols is what, maybe 10 or 11 US dollars?
Right around there. So you're talking about a 12 to 16% increase in the initial cost of your concrete.
That feels like a tough sell. When margins are tight, a 16% bump is significant.
It is. But this is where you have to look at the total cost of ownership. That small upfront investment is easily offset by extending the slab's life and, more importantly, avoiding huge repair bills down the line. This research gives you the hard data to justify that initial cost.
So to synthesize this whole deep dive, what we have is a brilliant case of researchers taking a global standard, the ASTM test, and adapting it to solve a very real, very expensive local problem.
It is. They prove that a moderate, precise dose of a common material, polypropylene fiber, gives you a technically superior result. It's applied science at its best.
And that brings us to our final provocative thought for you, our listener.
Remember how we talked about the lab conditions? They were brutal. The water evaporation rate they simulated was 20 to 35 times higher than what you would actually see in the real world in Juliaca.
So they tested it in a worst-case scenario that almost never happens.
Exactly. So here's the thought. Since the optimal mix, DMSO2, performs so well even under those extreme, unrealistic conditions, what deeper benefits might we see if it were used in a real large-scale building under normal conditions? Could the performance be even better? Could a return on that 16% investment be even greater than the lab results suggest? That's the mystery for the next team of engineers to solve.